Your app is not just storing data anymore. It is reacting to events as they happen. Every click, payment, login, message, and database update can become part of a live stream. And if that stream breaks, your entire system can fall out of sync. Welcome to an explainer that is going to fundamentally shift how you think about data architecture.
Today, we're talking about a massive paradigm shift in system design, removing away from the old-school idea that a database is just this static resting place for information. Instead, we need to start looking at data as a continuous, flowing river of events. We're going to see exactly how modern systems react to continuous change, how they keep dozens of microservices perfectly in sync, and how they transform raw live events into real-time derived data.
So, here's our roadmap for this explainer. First, we'll look at the real-time data problem. Then, logs and messaging systems. Why databases are actually streams. How to handle time, anomalies, and joins. Achieving fault tolerance and delivery guarantees. And finally, the overall stream processing paradigm. Let's get right into it.
The real-time data problem and what happens when things fall out of sync. Imagine this cinematic production crisis. Picture an e-commerce platform getting hammered with traffic. You're processing thousands of checkouts a second. Suddenly, your search index and your main database start lying to your users. Someone sees an item in stock on the search page, clicks it, and boom, it's sold out in the database. What went wrong? Well, look at how this timeline plays out. You've got client 1 and client 2 writing simultaneously. The database gets client 1's write first, then client 2's, so it settles on state B. But because of network quirks, the search index receives those exact same updates in reverse order. It processes B, then A. The systems have completely drifted out of sync, and without a reliable stream, they're probably going to stay broken forever.
Historically, the way we'd fix this mess is with batch processing. We'd basically just wait for a massive overnight job to scan the entire database, crunch all that historical bounded data, and overwrite the search index to fix the drift. But let's be real, impatient modern users are not going to wait until tomorrow for accurate inventory. That's where stream processing comes in. We need to handle unbounded, never-ending data continuously, reacting to events and fixing things the literal millisecond they happen.
Which brings us to Section 2, Logs and Messaging Systems, or how we actually go about taming this chaos. Because the big question is, how do we route millions of live events reliably?
How do we get data from our database to our search index without dropping things or scrambling the order? We introduce a messaging system. On one side, we have producers, like your app generating events. On the other side, consumers, like your search index. And right in the middle, connecting them, is the broker. But as an engineer, you immediately hit a wall. If your producers start blasting data way faster than the consumers can actually process it, what does that broker do? Does it just drop the messages? Does it buffer them in some giant memory queue? Or does it apply back pressure, basically yelling at the producer to slow down?
To answer that, you have to look at the type of broker you're using. Older, traditional message queues like AMQP or JMS systems are highly transient. The second a consumer reads a message, the broker deletes it. Poof, gone. But think about it. That is incredibly dangerous if our consumer crashes and we need to recover our system's history. That's exactly why modern architectures rely on log-based brokers like Apache Kafka. These are durable. They write every single message to disk in an append-only log, just like a literal file. They retain the history so we can go back and replay it whenever we want.
Think of these live events as moving dots. A log-based broker organizes all these dots into parallel highway lanes, which we call partitions. Producers are just constantly appending new events to the end of these lanes. Meanwhile, our consumers act like workers steadily reading down the lanes. And because that lane is a permanent, durable record, the consumer just uses a tiny bookmark called an offset to remember exactly where they left off. If a consumer completely crashes, no big deal. It wakes back up, checks its offset bookmark, and picks up exactly where it left off. Absolutely zero data is lost.
Moving to Section 3, databases are actually streams. This is the real paradigm shift. Now that we have our reliable highway, we need to talk about the biggest, best-kept secret in distributed systems. Your static database is kind of an illusion.
Whenever you update a row in a standard database, you overwrite the old data. You're maintaining mutable state. But when you do that, you completely destroy the history of how that data got there. The secret is, deep down, the database itself is actually writing every single change to an internal append-only log just to protect itself from crashes. If we can surface those immutable events and append them to an eternal change log, we preserve the true, chronological story of everything that has ever happened in our system.
This is where change data capture, or CDC, becomes an absolute game changer. Imagine CDC as a security camera pointed right at your database's internal log. Every single time a row gets inserted, updated, or deleted, CDC captures that exact change as a discrete event and fires it over to our log-based broker. Then, our search index or data warehouse just consumes that stream. Because the log enforces strict, unbending order, our search index applies the changes in the exact same sequence the database did. That nasty race condition from our earlier crisis, totally eliminated.
And we can actually push this philosophy even higher up the stack with something called event sourcing. While CDC extracts low-level database changes, event sourcing changes how the application itself behaves. Instead of your app running a command to just update row 5 to canceled, it explicitly records the user's intent. It saves student canceled enrollment as an immutable historical fact.
Let's trace a shopping cart timeline to see why this is so powerful. At time 1, an item gets added. At time 5, it gets removed. At time 10, the checkout completes. If you were just overwriting a database table this whole time, at the end, you'd just see an empty cart. You would literally never know the user almost bought that item. But by recording every add remove as an immutable event, you can debug exactly why a checkout failed. You can deeply analyze user behavior, or even build a totally new recommendation engine tomorrow just by replaying all that rich historical data.
This actually brings up a really beautiful mathematical analogy. Your current database state is simply the integral of your event stream over time. And conversely, the stream of events is the derivative of your state. State and streams aren't enemies, they're literally two sides of the same coin. The stream is the absolute truth, and your database is just a cached snapshot view of that truth at one specific moment. Once you start viewing data as a continuous stream, it unlocks some incredibly cool capabilities. We're not just syncing databases anymore. You can pipe these event streams into processors for instant credit card fraud detection. You can power live ticking dashboards, trigger immediate push notifications, keep massive search indexes fresh, and completely decouple complex microservices so they just communicate seamlessly through events. Section 4. Time, anomalies, and joins. Because as amazing as this sounds, reality is incredibly chaotic. Processing live, unbounded streams means you have to deal with the harsh realities of distributed systems. Networks lag, phones drop offline, and time itself gets really messy. One of the absolute biggest traps you can fall into here is confusing event time with processing time. Think about the Star Wars movies. Event time is the chronological timeline of the actual story, episodes 1, 2, 3, then 4, 5, 6. But processing time is the order they were actually released to the public, episodes 4, 5, 6, and then 1, 2, 3. If your stream processor groups data by the time it receives the event on the server, rather than when it actually occurred on the device, your calculations are going to be completely corrupted. Picture this scenario. A user taps checkout on their phone, but right at that exact second, they drive into a tunnel and lose their signal. Meanwhile, our server's stream processor is calculating total sales for that specific minute, and it eventually closes its time window. 5 minutes later, the user's phone gets a signal back, and that late event finally arrives at the server. A robust stream processing system absolutely has to handle these late, out-of-order, or missing events gracefully, usually by emitting an updated, corrected result for that older time window.
Things get even wilder when we need to combine streams. Stream joins are basically like two massive rivers merging. Say you want to join a blazing fast stream of user clicks with a CDC stream of user profile updates. To pull this off without terrible latency, the processor can't just pause and query a slow external database for every single click. Instead, it maintains a continually updated local state scoreboard, essentially a mini database sitting right inside the processor. So the second a click arrives, it instantly knows the user's latest profile data. Which brings us to Section 5, Fault Tolerance and Delivery. We have to address the elephant in the room, hardware fails. What happens if our stream processor, the one holding that vital local scoreboard, suddenly crashes mid-computation? Do we accidentally charge a user's credit card twice when the system reboots? This is where we have to define our delivery guarantees. At most once is super fast, but it means you might actually drop events. At least once guarantees you won't drop anything, but if a crash happens, a retry might cause those dreaded duplicate payments. To fix this, modern stream processors use continuous checkpointing, saving their exact offset and local state to durable storage, combined with idempotent writes. This achieves the holy grail, exactly once semantics. Even if the entire thing crashes, it resumes and outputs data as if the failure literally never happened. So, let's take a step back and look at our healed modern architecture. We have successfully unbundled the database. By stringing together change data capture, durable partitioned logs, and fault-tolerant stream processors, we guarantee that every single derived system, whether it's our search index, our analytics warehouse, or our live dashboards, perfectly understands the flow of change. They always stay perfectly in sync, no matter how much traffic spikes or what hardware crashes along the way.
Section 6. The stream processing paradigm. Ultimately, stream processing is not just about running batch jobs faster. It is a fundamental shift in how we model reality in our software. It is about building systems that understand change as it happens. So I'll leave you with this question. Look at your current architecture. Are you still just continuously overwriting the past? Or are you ready to finally harness the power of the stream?